Hello students. In the last few lectures, I have discussed about fluorescence spectroscopy. In the last lecture, I was discussing about steady state fluorescence. In this lecture, I will discuss about time resolved fluorescence spectroscopy. Time dependence of fluorescence can be described by fluorescence decay law, which I have already discussed to you when I explained how to get the lifetime from the fluorescence decay law, which is basically based on the first order kinetic equation. The fluorescence decay law assumes that a population of molecules is instantaneously excited when photons are absorbed, and then the fluorescence intensity gradually decays to the ground state. So, what you are basically looking at, that if there is n molecule in the excited state, on the absorption of photon, this molecule has gone from the ground state to excited state. So, how the population of this will decay with time, and the kinetic equation which has been used to know the number of excited molecule getting decayed with time is given by di by dt is proportional to I naught. Di by dt is proportional to I. So, what we can write is minus di by dt is equal to some constant k into I, where k is rate constant of the decay. So, you can simply write di by I is equal to k dt, and when you integrate this, what you are going to get is I is equal to I naught exponential minus t by tau, where tau is simply 1 by k. Tau is 1 by k. So, here what is assumed that the fluorescence decay follows first order kinetics, So, we can simply write minus di by dt is proportional to I. When you do that, what you get is this equation, and this is the intensity at time t, which is proportional to the number of molecules, number of fluorophores in the excited state at time t, and this is I naught is your number of excited state fluorophore when time is equal to 0. Now, the lifetime of a population of fluorophore is the time measured for number of excited molecules to decay exponentially to n by e of the original population via the loss of energy through fluorescence or non-radiative process. So, what I wrote is I is equal to I naught exponential minus k into t. This was the equation which we get when we solve the first order kinetic equation for the fluorescence decay. You can also write F is equal to F naught. It is quite same. Sometimes people write fluorescence intensity as F, or sometimes they write as I. So, F by F naught is equal to exponential minus kt, and you can also write F naught by F is equal to exponential simply kt, and this is nothing but n naught in the excited state by n naught, where n naught is your, or simply you can write n star divided by n. So, n star is number of excited fluorophore at time t is equal to 0, whereas n is number of number of fluorophore in excited state at time t is equal to t. So, this n star by n will be equal to exponential kT. So, what I am saying is that lifetime of a population of fluorophore is the time measured for number of excited molecule to decay exponentially to n by e of the original population. So, basically you can think of that n star by n star divided by e. This is your this thing, and this should be equal to exponential kT, and here this t is equal to your t is equal to, now in this case this is exponential k and simply tau. So, time, lifetime is time required for number of excited molecules to decay exponentially to n by e. Now, when you solve this, you will get E is equal to exponential k tau, and that simply means that k tau is equal to 1, and so tau is equal to 1 by k. So, sometimes this equation is also written like f is equal to f naught exponential minus t divided by tau, since k is equal to 1 by tau, k is equal to 1 by tau. So, this is the way lifetime is defined. So, again lifetime of a fluorophore is the time measured for the number of excited molecule to decay exponentially to n by e of the original population. Now, there are some very important facts about lifetime which you should know. Lifetime is an intrinsic property of a fluorophore and therefore does not depend on the method of measurement. So, this is very important property, and that gives you a tool to use this property in different kind of applications. The second important thing is fluorescence lifetime can be considered as a state function. If you have a slight idea of thermodynamics, you know what is the importance of a state function. So, fluorescence lifetime can be considered as a state function because it also does not depend on initial perturbation conditions such as wavelength of excitation, duration of light exposure, one or multi photon excitation, and also it is not affected by photo bleaching, which is not the case if you are dealing with fluorescence intensity, and that is why lifetime measurement is much more accurate comparison to compared to your fluorescence intensity measurement. In addition, fluorescence lifetime is a parameter largely independent of fluorescence intensity and fluorophore concentration. So, it does not matter what concentration of fluorophore you start with, lifetime is going to be same. Again, this is in contrast to fluorescence intensity. However, fluorescence lifetime can be sensitive to great variety of internal and external factors. Internal factors such as fluorophore structure, external factors such as temperature, polarity, and presence of fluorescence quencher. And that is why if I want to look at the effect of temperature, effect of polarity, effect of conformational change or binding, lifetime can be easily utilized. Lifetime concept of lifetime can be utilized to understand these effects. So, it is not dependent on concentration, but it is dependent on internal and external factor. Now, here is 3 examples which I will show. One is this dye, and this is ethidium bromide, this is ANS, and this is your tryptophan. These are the 3 fluorophores. Now, I will show you how its lifetime changes on change in the condition. here you see ANS in water is 100 picosecond. So, lifetime of ANS in water is 100 picosecond, but when it is bound to protein, the lifetime increases to 8 to 10 nanosecond, 8 to 10 nanosecond. Ethidium bromide, the lifetime is 1.8 nanosecond in water, but when it is bound to DNA, its lifetime is around 22 nanosecond, whereas if it is bound to tRNA, then its lifetime is 27 nanosecond. It is around 27 nanosecond. Now, lifetime of tryptophan can also vary, and people have observed lifetime of tryptophan in different proteins to range from 0.1 nanosecond up to 8 nanosecond. What does that mean is your lifetime is affected by the environment of the fluorophore, and this happens since in the condensed phase additional pathway due to interaction with molecular environment happens, and so lifetime may change. So, in different conditions there will be different pathways for energy transfers, and so lifetime will be different. Fluorescence lifetime tends to be shorter in more polar environment because of large dipole moments of surrounding molecules can increase the efficiency of energy transfer. So, these things are very important, that in the polar solvents lifetime tends to be smaller. In polar solvent or in the polar environment, your lifetime is going to be smaller, and so lifetime measurement can also give you idea about the environment of the fluorophore. What are the advantages of fluorescence lifetime measurement over intensity based measurement? One is that lifetime measurements do not require wavelength ratio metric probes to provide quantitative determination of many analytes. Similarly, lifetime methods expands the sensitivity of analyte concentration range by the use of probes with a spectral shift, and then lifetime measurement may be used for analyte for which there are no direct probes. This analyte includes glucose antigens or any affinity or immunoassay based on fluorescence energy transfer transduction mechanism. So, there are a lot of advantages of time resolved fluorescence over the steady state fluorescence. So, time resolved fluorescence spectroscopy is a quite powerful analysis tool in the fundamental physics, chemistry as well as in the life sciences. Now, how to measure the lifetime? It can be done in two ways. Lifetime measurement can be done either in frequency domain or the time domain, and I have already discussed about what is the difference between time domain spectroscopy and frequency domain spectroscopy. So, let us think about if I am trying to get lifetime using time domain method, what is the problems and what is the solution. So, first thing is, when we are trying to implement this in time domain, measurement of lifetime in the time domain, what we need generally is that we look at time dependent intensity profile of the emitted light upon excitation by a short flash of light, and typically we use a laser pulse. First of all, the decay to be recorded is very fast. It generally happens from picosecond to nanosecond range, and the typical fluorescence from commonly used organic fluorophore last only some 100 picosecond to some 10 of nanoseconds. So, the fluorescence lifetime is, or the fluorescence from a fluorophore generally lasts from 100 picosecond to some 10 of nanoseconds. So, what we need to do, if I want the not only to get fluorescence lifetime, but also the decay shape, it is very difficult to get it from a single excitation emission cycle. So, why we do need the decay shape? Because decay shape, if we analyze decay shape, then we can resolve multi-exponential decay. So, if there are more than one fluorophore in the system, then your decay will be your multi-exponential decay, and if we do not have decay shape, we cannot resolve multi-exponential decay. And so, one must be able to temporarily resolve the recorded signal at least to such an extent that the decay is represented by some tens of the sample. So, you need some point. So, suppose we decay started from this point and last to this point, then we need to measure several points in between. But since it is too fast in the one excitation and one emission cycle, it is very difficult to get 10 points between initial start and a final decay. So, for example, if the signal is 500 picosecond long, so from the excitation to emission decay to 0, if suppose this is 500 picosecond long, then signal would have to be sampled at the time step of say 10 picoseconds. So, that we have almost 50 data. So, between this we need to get several points such that we can know what is the decay shape, and then we will be able to resolve multi-exponential decay. Optical signal may consist of just a few photon per excitation emission cycle, and so the discrete nature of signal itself prohibits analog sampling. So, suppose we want to do analog sampling, the discrete nature of signal will prohibit the analog sampling. So, one way we can think of that, okay, let us increase the excitation power to obtain more fluorescence light, but there will be limits because of collection, there can be optic losses, and then there are spectral limits of detector sensitivity. And if I use higher excitation power, then there is a chance of photo bleaching. And so, these are the problems associated with single excitation emission cycle. So, problem can arise when the observed sample consists of just a few or even single molecule, and that is the situation commonly found in confocal microscopy applications. Now, what is the solution? Solution of this is using the method called TCSPC, which stands for time correlated single photon counting. So, in this we do not use only one single excitation emission cycle. Here we do periodic excitations from a laser, and then we can extend the data collection over multiple cycles of excitation emission. One can then accept the sparseness of the collected photons and reconstruct the fluorescence decay profile from the multitude of the single photons event collected over many cycles. I will explain this line in the next slide. So, this is the way we basically doing time correlated single photon counting. What we are doing, that this is source of light, and here a fluorophore from the ground state goes to excited state, and then you are detecting photons. When photons, you come across a photon, this will stop, and time digitizer will tell you the time gap when you receive one of the photon, and then number of photons seen versus time, which is called lag time, is basically plotted in this. Again you see next one, then it will be more clear. So, what we do in this is, first we applied laser pulse. So, we applied laser pulse and then we started looking for photon. Suppose photon comes at this, which is around 3.4 nanosecond. So, between this when you excited and this one when you observed a photon, the time gap is 3.4 nanosecond, and that is what you are plotting. So, one photon at 3.4 nanosecond. Now, look at this, again I excited, but there is no photon in between. So, within this period I did not see any photon. Again I excited. So, multiple excitation is going on. So, again I excited and I did see a photon when the time gap between these two is 4.7 nanosecond. So, what we do is we repeat this cycle, and then here is your different cycles and when did you see the photon. So, what will happen that in first cycle I did not see a photon, in the second cycle I did see here with the time nanosecond in this nanosecond, third I did not see, fourth I did see at this point, 5 I did see at this point, in 9 I did see at this point, and n I see at this point. Now, what I will do is I will look at photon distribution between a small gap of time. So, what you will get is this kind of profile, So, initially this intensity increases and basically number of photon increases, then there will be a decay. What does that mean is in this period, after this you will see that within this range of nanosecond there is a less number of photons seen. But you have to do this several thousands of times, so that you can get a very nice photon distribution curve. Now, you have this curve and now you can just fit it and see what is the lifetime. So, this is the time domain data, this is the excitation pulse, and this is your fluorescence decay. As I discussed with you, this is IT will be given by this equation. So, IT is equal to I naught into exponential minus t divided by tau. If there is only one fluorophore, and that one fluorophore has only one lifetime, then you will get this kind of curve. This is when there is more than one lifetime, and that can be because of, suppose if you are discussing protein, there may be 2 tryptophan which is undergoing decay, and so there will be some from 2 different tryptophans. Also, it may be because of there is only one tryptophan, but it is changing conformation between 2 different conformers. For example, native state with the denatured state, tryptophan in native state and tryptophan in denatured state, and there is equilibrium between 2 different conformation of proteins or 2 different conformation of fluorophore, then you can get this kind of data. So, we can calculate the mean lifetime, and mean lifetime is calculated using, if you understand If you remember your quantum, what you have studied in the BSc courses, you will remember how to get the lifetime. It is simply 0 to infinity t multiplied by IT dt divided by 0 to infinity IT dt. So, this is the way you calculate your lifetime of a fluorophore. Now, the second way of measurement of lifetime is by using frequency modulated lifetime technique. What you do in this is the sample is excited with the light that is intensity modulated at a high frequency comparable to the reciprocal of the lifetime. So, that is what we do. Then what you will see, you look at the emitted light. The fluorescence emitted by the fluorophore is going to have a similar waveform and same frequency as the incident light, but is modulated and phase shifted from the excitation source spectrum. So, what here we are looking at is the time delay here is measured as a phase angle shift between excitation and emission. So, what we did, first we excited the fluorophore with the light which is intensity modulated, and now we are looking at the fluorescence emitted. Fluorescence emitted which has the same frequency, only thing is it is phase shifted from the excitation source spectrum and is modulated. And now we are measuring the difference between phase. So, if I can measure phase angle shift between excitation and emission, then I can calculate what is the lifetime. Similarly, the peak to peak height of the modulated emission generally decreases, is decreased relative to modulated excitation, and that also gives you another independent measure of the lifetime. So, phase angle is related to the lifetime, and also the modulation peak to peak height of the modulated emission is also related to the lifetime. Now, let us now understand what is basically happening. So, as I told you that we are using the intensity modulated light. So, the excitation is assumed to be sinusoidally modulated light. What does that mean is that this is given by A plus A sin omega t. So, this is capital A plus small a sin omega t, capital A plus A sin omega t. So, what does that mean is when we have omega t is equal to 0, then we have f t is equal to A, because this sin term will be 0, and when omega t is equal to pi by 2, then we have f t is equal to A plus A. So, when omega t is 0, then f t is equal to A. When omega t is equal to pi by 2, then this value sin omega t becomes 1 and A into sin omega t becomes A. Here omega is the angular frequency of modulation, and A by A, this ratio small a by capital A is basically known as modulation of incident light. Now, let us talk about the emission. So, fluorescence emission responds to same frequency with phase shift and modulation. Then the excited state population is given by Nt is equal to B plus small b sin omega t minus phi. Now, you can see the frequency is same. What is different? There is a phase shift, where phi is your phase shift, and the modulation is also different, and now modulation is B divided by B. Now, you can think of this is also same kind of curve, only thing in now omega t minus phi will be 0, then your Nt will be equal to 0, then Nt will be equal to B. And when omega t minus phi is equal to pi by 2, then Nt is equal to or a small big B, capital B plus a small b. So, sin pi by 2 will be equal to 1, and then. So, these are the two different curves. You keep in mind what are the equations I have given. So, this is basically your intensity versus time profile. This is your excitation pulse, intensity modulated excitation pulse, and this is your emitted fluorescence. Now, see here, if you look at this, this is basically amplitude is 0 here, and so you see, if you remember what I told, that this is given by the equation Ft is equal to A plus A sin omega t, am I right? So, if omega t is 0, then Ft is equal to A. So, Ft is equal to A. Look, this is your intensity which is equal to A. Now, and this is, you remember, any wave starts from this point, am I right? Wave goes like this and then comes back and then goes like this. So, this is when our omega t is equal to 0, then you have Ft is equal to A. Now, omega t is equal to pi by 2 here, am I right? So, omega t is equal to pi by 2, then Ft will be A plus A when you have omega t is equal to pi by 2, and that is what you can see here. This is whole intensity is A, capital A plus a small a, capital A plus a small a. And now, if you remember, then what is the modulation? Small a by a. So, this is a small a by a is the modulation. The small a by a is the modulation for this excited pulse. Now, let us look at the emitted light. Here, if you look at, there is a phase shift is this. This is your phase shift phi. Okay. So, if you go from this point, so suppose this point to this point, there is a shift of this point to this point, right? There is shift of phi. And so at this point, omega t minus phi is going to be 0. Omega t minus phi is going to be 0. Okay, omega t minus phi is going to be 0. In that case, if you remember that in this case, your intensity Ft is given by your, or not Ft, you just write fluorescence, or N star is basically given by your B plus B, or let us see, B plus B sin omega t minus phi, sin omega t minus phi. So, if this is 0, then this is equal to B, and if this is 1, then whole thing will be B, capital B plus a small b. So, this will tell you about what is the principle behind frequency modulated lifetime measurement. What we need to do is, we need to measure this phi, or we need to measure this B factor, because phi and this m value is related to the lifetime. And the way we can do is given in this slide. So, if we consider single exponential decay, the time independent or time dependent intensity will be described by this first order differential equation, which is dN by dt is equal to k into Nt plus Ft. And if you remember that what we are talking about, this is your Ft which basically increases the number of photons in number of fluorophore in the excited state, and this is the NT, which is number of fluorophore in excited state. So, if I am applying pulse, Ft will increase the population of excited state, and the population will decrease because of your fluorescence, and the decrease in the population of excited state is your proportional to number of fluorophore in the excited state, and so you have minus K into NT. So, this tells you about a decrease in fluorescence with time due to emission, and this tells you increase in number of excited state, number of fluorophore in excited state with time due to excitation. Again, this term tells you number of your increase in number of excited number of fluorophore in the excited state, and this tells you increase in number of fluorophore in excited state due to excitation, and this is your decrease in number of fluorophore in excited state due to emission. So, there are two terms. We know that this rate constant is equal to 1 by lifetime, and that is what we have written here. So, K is equal to 1 by tau. So, this equation dN by dt can be written as equal to minus NT divided by tau plus Ft. Now, if you remember, N is given by B plus B sin omega t minus phi. So, dN by dt will be equal to B omega cos omega t minus phi, and now minus K NT. NT is, here I have missed this, so minus B plus B sin omega t minus phi by tau plus Ft is equal to A plus A sin omega t, And from the above equation, one can obtain the familiar relationship between phase shift and fluorescence lifetime, as well as relationship between modulation depth and fluorescence lifetime. So, tan phi is equal to omega t, and this we can get from this equation. If we solve this equation, we can get the value of tan phi gives is equal to omega into tau, tau is your lifetime, and B divided by B and divided by A will be equal to M, and that will also give you tau. You can get the value of lifetime from the phase shift, or you can get the value of lifetime from the M value, The problem with this method is it does not provide a direct information on the shape of the fluorescence decay. I told you there are two ways in which we can get the value of tau. One is through the phase shift, and another is through the what is called demodulation parameter. If the tau obtained by two equations are equal, then it indicates there is a single exponential decay, but if it is not equal, then it means there is a complex decay and we need to use different equations. Time resolved measurement, whether performed in time domain or in the frequency domain, provides information about intensity decay of the sample. Samples with multiple fluorescence typically display multi-exponential decay. Even samples with a single fluorescence can display complex intensity decay due to conformational heterogeneity. So, it is not true that if there is a single fluorescence, then it will always show single exponential decay. It may show a complex intensity decay because of conformational heterogeneity. So, fluorophore are in different conformations in the same sample. There can be resonance energy transfer and the transient effect in diffusive quenching or fluorophore solvent interaction. So, there are some of the origins why a single fluorophore can display complex intensity decay. So, advantage of lifetime measurement is lifetime measurement can tell you how each of the fluorophore is affected by interaction if there are more than one fluorophore, which is not possible when we are trying to study the fluorescence by steady state fluorescence measurement. It can also distinguish between static and dynamic quenching. In static quenching, a fluorophore in excited state does not interact with the quencher. Quencher interacts with fluorophore in the ground state. So, in the static quenching, there is no change in lifetime in presence or in absence of a quencher. Whereas, in dynamic quenching, quencher is associating with fluorophore in the excited state, and hence hence the lifetime changes when you have a dynamic quenching. The third important thing is that resonance energy transfer can also be best studied using lifetime measurement. Fluorescence lifetime are typically independent of probe concentration, and so they are often used for cellular imaging. Now, what is the importance of lifetime measurement? It can tell you about the changes in environment. For example, if there is a change in viscosity, there is a change in pH, there is change in polarity and change in solvation, because these factors affect the lifetime. And so, we can tell about changes in these physical parameters by measuring the lifetime. We can also talk about size and shape of the molecule. We can talk about molecular interaction, because lifetime measurement can give you idea about static or dynamic quenching, and similarly for freight measurement we can apply your lifetime measurement. It also gives you inter and intramolecular distances. Again, this can be done by measuring transfer efficiency using lifetime measurement. And then we can also see the kinetic and dynamic rates. We can get the resolution of molecular mixtures using lifetime measurement. I will give you some applications of the lifetime measurement, and this is your anion sensing by MQAE dye. MQAE is basically N-ethoxycarbonyl methyl 6-methoxyquinolinium bromide dye. It is quite sensitive to chloride ion, and here I can show you that in presence of 0 millimolar chloride ion, the lifetime is 5.8 nanosecond, whereas in 75 millimolar chloride ion, it is 3.5 nanosecond. So, if you increase the concentration, lifetime of your MQAE dye decreases. MQAE dye decreases, and that is how we can detect chloride ion, and we can also talk about concentration of the chloride ion in this case. There is another application where we see we are trying to measure pH by a fluorophore called fluorescence. And fluorescence lifetime is also dependent on pH, and this is your tau versus pH for fluorescence, and you can see that it is increasing on increasing the pH. So, what we did here, simply we are exciting fluorescence and looking at the decay, and from the decay you get the tau, which is in nanosecond, and now you are plotting at the various pH, and what has been seen that pH can be sensed by fluorescence if we use lifetime measurement, if we can make lifetime measurement, and your lifetime is going to be different, lifetime of this fluorophore is going to be different in different pH. Now, another application is your oxygen sensing by pyrene. Pyrene is another fluorophore which senses oxygen, which is used for sensing oxygen. And this is your Stern-Volmer plot. Again, you can see that we can look at the lifetime measurement versus oxygen, and you can see that this is basically increasing. So, again here you are looking at the quenching by oxygen. Here we are looking at quenching of fluorescence of pyrene in the presence of oxygen. So, oxygen is acting as a quencher, and Stern-Volmer plots is given here, and that can give you the value of KSB. Now, this is one example where labeled peptide, the labeled peptide is studied by your time resolved fluorescence. So, this peptide is labeled with rhodamine, and this is the peptide and this is the rhodamine. It has weak fluorescence when it is not cleaved, but if I cleave it, then there is a strong fluorescence which is shown here. So, this is a strong fluorescence when it is cleaved, and this is weak fluorescence when it is not cleaved. Now, if I look at the fluorescence, if I just look at fluorescence intensity, what we are going to see that it is cleaved or it is not cleaved. So, this is the rhodamine labeled peptide. It has two lifetime, or it is basically bi-exponential. Its fluorescence decay is basically bi-exponential. So, one lifetime is 2.44 nanosecond, another lifetime is 0.14 nanosecond. 0.14 nanosecond, the percentage or F1 is basically 0.95, here F2 is 0.05. So, fluorophore, most of the fluorophore decays with this lifetime, only 5% of fluorophore decay by this lifetime. What does this tells you? That the peptide, when it is not cleaved, has two conformations. It is going into two conformations. It has two conformations. One conformation contributes 95%, another conformation contributes 5%. This kind of information you cannot get from steady state fluorescence measurement or intensity measurement. This can only be obtained by lifetime measurement. So, this lifetime measurement tells you that 95% of the fluorophore is in one conformation with the lifetime 2.44 nanosecond, and the 5% are in the conformation which has lifetime 0.14 nanosecond. Now, when you clip this with this enzyme pronase, what you are going to get is only one conformation. You see, it can be fitted only by single exponential, and all the fluorophore is now decaying with the 2.43 nanosecond lifetime, which is quite close to this one. And so, what kind of information we got? That the uncleaved peptide is an equilibrium between two conformations, but when I cut through pronase, it gives you only one conformation with the lifetime 2.43. This is the data, same data, but labeling with 6-rhodamine, and when you do that, again you see same kind of conformation, and when the information you get that again peptide is basically, intact peptide is basically a mixture of two different conformation, and when we cut it, then again we are getting only one conformation with single lifetime. Now, what we are going to see is the effect of freight on the lifetime, effect of freight on the lifetime. So, this is important if I want to study the protein ligand interaction or protein protein interaction using lifetime measurement. So, now you see that this is your donor, this is acceptor. When you put light, then what will happen? It goes to excited state, it comes back, and there is a transfer, non-radiative transfer to acceptor. What it does? It excites one of the your fluorophore to the excited state, and then what happens? That this is same acceptor, there is emission of the photon due to fluorophore coming from excited state to ground state, and this being radiative transition, this being radiative transition. Now, here transfer efficiency can also be given in terms of lifetime, and transfer efficiency is equal to 1 minus lifetime for donor in presence of acceptor, and this is your lifetime of donor. So, what is the freight effect on lifetime? So, if there is no freight, then donor undergoes slow decay. When there is a freight, donor undergoes fast decay. So, just by looking at the lifetime, you can know what is the you can know whether interaction between two proteins is taking place or not, and that gives you a very useful applications. You can even calculate fraction of interacting molecule. So, suppose there is a donor, when it is not interacting, then this is your decay profile, and you can see this is slow decay. But if they are interacting, then this donor goes a fast decay. So, the double exponential decay profile are due to presence of an interacting and a non-interacting donor fraction. So, if you see donor which is interacting at this profile, donor which is not interacting at this profile. So, if there is a mixture of your interacting fluorophore and non-interacting, then you will get this kind of curve, which will be bi-exponential, and just by analyzing this and taking the ratio of A1 and A2, we can know what is the fraction of interacting molecule. So, true freight efficiency for the interacting proteins, the ratio of the distance and the Forster radius, and the ratio of relative numbers of interacting and non-interacting donor molecule can be derived from these parameters. So, I think I am now done with the lifetime measurements. So, today we discussed about the lifetime measurements, what are the different methods to get the lifetime, and lifetime as very important applications. We saw how lifetime can be used for various applications. I also discussed about the combination of freight or getting information from freight using lifetime measurement, and that can be utilized to understand the interaction between two different molecules. We can also do microscopy using these techniques, but I will discuss microscopy in the next lecture. The two your books and notes which I referred for making the slides are your tech notes on TCS PC from PicoQuant and the fluorescence light measurement and biological imaging. This is a review and chemical review, and this is your detail about this paper. So, thank you very much for listening. See you.